Hello guys, I'm Aditya C, 19 BPS 1069 and I'm a student studying in Velu Institute of Technology. Now, I'm going to present about SHA Fighter algorithm with an example for my digital assignment 3 for the course Blockchain and Cryptocurrency Technologies. Now, let us see what is SHA. SHA, or also known as secure hash algorithms, are a family of cryptographic hash functions published by the National Institute of Standards and Technology as US Federal Information Standards. SHA is divided into four broad types, namely SHA-0, SHA-1, SHA-2, and SHA-3. SHA-0 is the initial SHA, which was developed in the 1990s and it was immediately discontinued as a significant flaw was discovered by the US National Institute of Standards and Technology, and it didn't cause lots of problems. SHA-1. SHA-1 is also similar to SHA-0, but it was designed by the National Security Agency and to be part of the digital signature algorithm. Now, as moved on, the SHA-1 was failed a lot of tests and many weaknesses were discovered. And in 2010, the use was not recommended by the National Institute of Standards and Technology. Coming to SHA-2. SHA-2 is broadly divided into SHA-256 and SHA-512. Now we are going to see into SHA-512. To hash a message with the SHA-512 algorithm, we need to follow four steps. The first step being input formatting, followed by hash buffer initialization, then message processing and delivering the output. Now let us consider an example message ABC, small letters. We are going to hash this message into a 512-bit answer and let's see how it transforms. Now, uh, the SHA-512 can't hash a message of any size because it will be disuniform and it will be very difficult to hash messages of different sizes. So the message size must be uniform and the entire, so we do input formatting and the input formatting consists of padding and at the end uh, we append the size of the message in the form of hexadecimal for the last 120 bits, and they should all have a combined size of a multiple of 1024 bits. Now for example, let us take a message ABC. The ABC message is 97, 98, 99 in ASCII. Now translating it into hexadecimal results in the value of 61, 62, 63 as the message. Now, as each hexadecimal digit occupies 4 bits, the length of the message is 4 into 6 digits, which is 24 bits, and converting 24 bits to hexadecimal is 18. So, the length of the message, that is the size of the message L, is 18. Now, let us see the message after input formatting. The first 6 digits are the message 61, 62, and 63. Then, after the message, we need to insert a padding starting with 1 followed by a bunch of zeros. The We start with the 1 and a bunch of end with a bunch of zeros so as to indicate the padding has started and it is not the message content itself. Now, the binary value of 8 is 0100, so sorry 1000, so we start with an 8 and it goes on till the end, and the last two rows or the last 128 bits are reserved for the length of the message as said in a previous slide. And as we calculated previously, the length of the message is 18, that is 24 bits and is in hexadecimal, so we will append a bunch of zeros and 18 at the end. Now coming to the second step, hash buffer initialization. Now there are 8 registers in the hash buffer which are transformed during the 80 rounds of a hash SHA 512 algorithm. Each each block is named between A to H. Now the respective ith block is initialized with the initial value corresponding to the first 128 bits of the fractional part of the square root of the ith prime. For example, The first block, register A, has a hash initialized value of 0x6809, etc. This is the fractional part of the square root of 2, which is the first parameter. The square root of 2 being 1.414, and if you convert the 414, etc., to hexadecimal, the resulting value is 6809866. Now this continues till b to h. B being the fractional part of square root of 3, C for 5, D for 7, E for 11, F for 13, G for 17, and H for 19. Now, coming to a third step. After we will process the message by taking it through 80 rounds of transformation with necessary inputs from the previous rounds. Message processing is done upon the formatted input by taking one block of the 1024 bits at a time. The thousand, the actual processing takes place by using two things: the 1024 bit block and the result from the previous processing. And before finalizing the hash value, the message is processed up to 80 rounds. Now, when you look at this message, there are you can see two parts: W0, K0, W1, K1, WT, KT, and W78, K78. W0 is nothing but a part of the message. It is called as a word, and K0 is nothing but key. Uh, I'll explain about W0 and K0 in the next slide. Now, words W0 to W79 and keys K0 to K79. Words are part of the message, mutated into blocks of each of size 64 bits. Now, let us take an example. W0 to W50. As the message is 1024 bits, and if you divide 1024 by 64, you get 16. So the first 16 words are just the 16 parts of the message itself. So W0 to W15 is the parts of the message. Then after W15, you follow a formula. The formula being WT equals to sigma 512 to the base 1, WT of T minus 2 plus WT minus 7 plus sigma 512 base 0, WT minus 15 plus WT minus 16. The sigma 0 of phi 12 is defined as rotate right once of x, XOR rotate right 8 times of x, then XOR shift right 7 times of x. Now, sigma 1 phi 12 of x is rotate right 19 times x, XOR rotate right 61 times of x, XOR shift right 6 times of x. Now coming to keys. Keys are 80 separate large numbers which was generated by the NIST for the cause of SHA. The method of generation of keys is still secret to the public and nobody knows how it came to existence. We just have the keys and we use it for hash algorithms. Now coming to the each iteration values. These are the 8 hash buffers A to H. Now let us consider this as round 0 and let us consider this as round 1. Now, to find out the values of A to H in round 1 from round 0, you do a bunch of operations. Now, let us follow the arrows. The value of A in the previous round, that is round 0, goes to B in the round 1. Similarly, the value of B in round 0 goes to C, and C to D, and E to F, F to G, and G to H. Now, there is changes in A and E. Now, to get A for next round, you add the previous round's A with the majority of A, B, and C. That is the maximum number of A, B, and C. And then you add this. And this is a composite of KT. KT is nothing but the key of Tth round. That is K0 or K. Now, if you add these three, you will get the value of A for the next one. Now, coming to E. For E, you add D and and you add KT with all these values with H and the CH of EFG. Now, the CH is the choice function. Now, This is just a conditional function. That is, if e is true, that is, if e value is 1, then take f, or if a e value is 0, then take g. Then you add these values with wt, kt, and you add d to it to get e. Now the process continues through 80 rounds, and the output of the final round is as shown below: 73A54F etc. to 1CE8326. Now, if we go to the previous slide, you can see that in the final answer, you add the result of the round 79 to the initial hash values. That is the initialized hash values of the square root of prime numbers. That thing. Now the hash value is added like as such. So 6809E66 is the hash value of square root of, I mean the initialized value of the fraction part of square root of 2 plus the first 64 bits of this value. So then this results in DDAF. Like this, you repeat it for 8 different values and you will get 8 times 64 bits. That is a total of 512 bits of answer. Now, the resulting 512 bits hash message is the combination of these 8 uh, into 64 bits into one message. See the drastic changes of the just the message ABC. The ABC is practically uh, undecryptable now.